first, as I said, I'm going to give an introduction to some of the background, the motivation behind the project. So just to talk a little bit about the large-scale project that we're a part of, which is the IOF 2020 project, which is the Internet of Food and Farm 2020. This is a large-scale European-funded project. It's got 73 partners. It has a budget of 30 million euros. Some of the numbers there are on the screen. We have 5 trial sets, 19 use cases, but I'll go through some of this. So, okay, so the objectives of IOF 2020 are, the main objective is to foster a large-scale take-up of Internet of Things in European farming and food production. And there are sub-objectives to demonstrate the business case for IoT in a large number of areas in the farming and food, to integrate and reuse IoT technologies by exploiting open architectures and standards, and to ensure user acceptability of these solutions by meeting user needs, including security, privacy, and trust. And finally, to ensure the sustainability of these solutions by validating the related business models and setting up an ecosystem to accelerate large-scale adoption. So there are 5 various use cases spread across Europe and beyond, actually. So we have use cases for trials, dairy, arable, meat, and vegetables. We're part of the dairy trials, and you can see where the dairy trials are located in Europe. But we also have a location in Israel, which is not on this actual map here. So we take a multi-partner approach. So we have farmers, producers all along the supply chain, IoT integrators, IoT vendors, infrastructure providers, and academia. And all of these partners are part of the use cases. The methodology is generally MVP driven and includes end user feedback, which informs improvements and future feature selection. And this is then evaluated through KPI evaluation, and we continue through this MVP cycle to large-scale demonstrations. This is all framed within a work package called Work Package 2 Trials and Use Cases, Knowledge and App Development. So this is where we belong. These are the supporting work packages around that. So we have IoT integration, business support, and ecosystem development. And all of this is within the framework of the IOF 2020 ecosystem and collaboration space, managed by Wageningen out of Belgium. Out of the Netherlands, I beg your pardon, out of the Netherlands. Okay. So we're part of the dairy trial largely. This started with 4 use cases: the grazing cow monitor in Belgium, happy cow also in Belgium, herdsman in Scotland, remote milk quality in the Netherlands. And there was an open call after 20 months of the project where they asked for further use cases to be part of the project, and we applied to that, and this is how we actually became part of IOF 2020. So the project itself is 48 months. We've been part of the project since January 2019, and our participation was finalized in October 2020. So we effectively had 22 months. So we're part of this open call. We're MELD, early lameness detection through machine learning. And I'll just now give an overview of MELD. So MELD is concerned with lameness detection in dairy herds. We estimate that the lameness can cost the Irish farmers in total 80 million euros per year just in the dairy area, not including beef. This is a problem canvas that we developed just to give a kind of background. So the problem space is in lameness in farm animals, primarily in dairy cattle, and lameness represents the 3rd biggest known problem in dairy herd management. Now, the traditional alternatives are end user with visual observation, treatment through veterinary intervention, antibiotics, and segregation of animals. The shortcomings there are that there's a labor overhead, there's a cost, there's reduced animal welfare. Our goal is to, what we have achieved actually is detecting lameness 3 days in advance of the farmer actually detecting it through visual observation. So the quantifiable impact, the estimate for a lameness instance is the cost is €275 in dairy cattle. So we look to reduce that cost and increase milk yield. So the problem becomes when oftentimes if you have to administer antibiotic, the animal needs to be segregated from the herd, and that milk can no longer be used, and that's the primary cost. So the challenge is to help the farmer in the identification of lame cattle earlier than this visual observation, and this will reduce the cost of lameness, increase the animal welfare with reduced antibiotic usage. And our solution is to take established bovine monitoring technologies, and we provide an over-the-top service on that. So these monitoring technologies generally work something like this, where there are sensors on the animal. These sensors are fed into some back end, sometimes locally, sometimes in the cloud. And then the farmer is given information based on some analysis of that data. So we provide an over-the-top service that provides a cloud-based machine learning algorithm. We use the data that's been collected by the established bovine monitoring technology. We do some analysis in the cloud. We provide the farmer with lameness alerts where we've detected lameness. And based on the feedback from the farmer, we can retrain this model and make a personalized model for that specific farm. So we have individual models for each individual farm. This gives a kind of infographic of our overall system, and it breaks it down into subsections and how we actually operate. So this is the ecosystem. This is the world we work in. These are dairy herds out in the pastures, and in some of our trials, they're actually barn-based, shed-based. So we install, in one case, we have two vendors. One of our vendors has foot-based long-range pedometers, and our other vendor, Herdsy, have collar-based sensors. So based on the data that's extracted from these sensors, we provide some machine learning models in the cloud, and this is what Mohit is going to speak about in a little while. Then this provides value to the farmer via a mobile app where we receive feedback from the farmer. And I'll talk a little bit about that once Mohit has completed his part. So if I hand over to Mohit, he's going to speak about this, this element here up in the top right, which is the machine learning model.
Thanks, Paul. I'm just going to share my screen. Yeah, my screen is visible, I believe. Yeah. Thanks, everyone. Good morning. My name is Mohit Taneja. I'm going to talk about the data analytics side of the project. So in the data, we use three features, which is one is step count, another one is line time, and another one is swaps, that is used to train the machine learning model that Paul mentioned. This is a representation of the data that is collected from the pedometers at a PC form factor device on the farm. And this is summed up on hourly basis. This is represented for one animal, 2636 in 2017. So the background of the project came from our work in Smarter project on which MELD followed. So this is the machine learning model pipeline that is used, that was used to develop the machine learning model. So first we collect the data from the sensors, and then there was an animal expert who did the visual inspection on the data, and the locomotion score that was followed for doing visual inspection, it is as follows, which is from 1 to 4, where 1 and 2 stands for normal and mildly lame, and in our case they act as non-lame, and 3 and 4 stands for lame and severely lame, and which for us act as lame, and that makes us the binary class for these two classes. And then we basically translate this human expertise into a machine learning model, which is scalable enough, and then it can be catered to different farm premises. And then that led us to the project of early lameness detection. So going deeper into the data side, this is the representation of, for one particular animal, cow 2346, and it's a time series based activity representation for the three activities: line, steps, and swaps. So the first idea, the first step in segregating these two parts was to divide this activity of the animal once it has been observed by the animal expert into two parts. So here you can see we checked as the normal activity region and lame activity region. So given that lameness is a transition, so this D1 act as the day when the animal expert identified the animal to be lame. So all the activity prior to that act as the normal activity region for the animal, and all the activity after that acts as lame activity region for the animal until the day the animal is out of the lameness cycle. Based on this, for the animals in the herd, we made two distribution in for the animals in the herd, and these two distributions are normal profile and lame profile. And normal profile are the animals which are non-lame at a given instance of time, and lame profile are the profile of the animals which are lame in the same time period. And that we found that there are two distinct profiles that exist within a herd, and these are the representation of these profiles with respect to the density function and the mean absolute deviation. Our next step was to compare how the distribution of each and every individual animal compares to these two distribution, given that lameness is a transition from normal condition, which is non-lame condition, to lame condition, and then back to normal. So we compared it for each and every animal over a sliding window period. So over here, we take the same animal again, which is 2, 3, 4, 6, and we compare its distribution when it is normal and when it is going to lame. And while doing this analysis, we found that there is no one way where the animal which is going from normal condition to lame condition, they will translate or they will move along this path in the same way. So each and every animal had either one hump in this and then the other hump in the lame distribution. So each and every animal, when it went from normal to lameness cycle, it behaved differently. And uh, for that, we again compared the day-to-day activity of any two cows through observation, and it was visible that any two animals within the herd, they behave separately, and that for that we had to do kind of animal profile specification to develop a machine learning model. And that led us to the conclusion that there is no one-size-fits-all solution where you will treat all the animals in a respective herd size as a singular unit, and then you will train the machine learning model, which will act kind of a uniform basis for all the animals in the herd. And that led us to identifying activity clusters within the herd, which is backed up by literature as well. So we used herd mean as the baseline, and we identified 3 activity clusters in the herd: active, normal, and dormant. Active are the animals whose activity levels for any of the two activities is always higher than the herd mean. Normal are the animals whose activity levels are always tracing the herd mean, and dormant are the animals whose activity levels are always below the herd mean. And we also found through the observation that these groups are dynamic at any point of time. An animal can move and can migrate from one cluster to another cluster, so they need to be reclustered periodically. And the time period that was found for this periodic reclustering was 2 weeks, which is 14 days. At the time of the model development, where MELD started, this was the distribution of the animals in these 3 different activity clusters. So this is the hybrid model that was developed for early lameness detection, where we first take the cow activity data, and in that activity data, we use these 3 features: step count, line time, and swaps. And then we make these 3 different clusters, which is active, normal, and dormant. And then for each of these clusters separately, we developed one model for each of these clusters: one for active, one for normal, and one for dormant. And then that model goes into training, and once it is evaluated, it goes into production. And then based on this iterative feedback, we retrain the model if it needs to be. SN and SL here represents the set of normal activity region points for non-lame activity region, and SL represents for the lame activity region, which was used for training the model. So these were the result of the classification algorithm, which were balanced in terms of accuracy, precision, and early lameness detection. So we started with k-nearest neighbor, which gave us accuracy and respectable early lameness detection measured for the project. And these are a few of the results where we went back into time and see like when it was observed by the animal expert or the farmer, and when the model detected the animal to be lame. So for this behavioral analysis, we primarily have 2 parts, where we first cluster the animals, and then the second part is where we classify the animal to be lame or non-lame within the herd. In MELD, we further automated the process of classification of automating the classification methodology using different feedback iteration mechanism. So the feedback that was used for improving the classification model and automating the process was through the mobile application, about which Paul is going to talk in the next few minutes. So over here, because there's no specific visual frequent observation, so the feedback from the farmer act as the methodology to improve and automate the classification methodology of the model. While doing this, the main objective was to reduce the daily false positives that were being reported to the farmer, while maintaining a good balance of accuracy and precision, so as to give an improved user experience to the farmer. Now, this connects to a problem, a kind of a classical problem in the data science domain, which is the data set shift setting problem, which is sometimes overlooked. So what happens is that on a single day, you will have more non-lame animals than lame animals. So at a single day, if you compare it as a stationary and non-stationary time series, so you will find that you will have kind of an unbalanced data set on a single day while you are acting them as the query points to your model. So our idea was to make it well balanced with maintaining a good accuracy and precision for a better user experience. So these were the further different classification methodologies that were implemented in MELD, which included KNN, support vector machine, logistic regression. And there were reasons behind using these different methodologies, given that we were limited to 3 feature space. So doing any feature space mapping and feature engineering was limited with the availability of the data and the limitation to the 3 features. And the last methodology that was tried was Lameness transition probability approach, which is posing the problem as a regression problem and then using the probability score index for binary classification. Based on these, we trained different models, starting as a global model that was developed in the background project Smart Herd. And then based on so our idea was to compare different farm data distributions so as to have a farm specific model selection. So first we introduced a distribution comparison, which is for per farm. And then we use, based on the available models, we select a model that goes into the production and that works with the end-to-end software solution. By the end of the project, these were the representational accuracy that came from both of the approaches, which result in the same accuracy and reduction of daily false positive. One is k-nearest neighbor to specific hyperparameters, and lameness transition probability approach, which resulted in an overall accuracy of 89% with a reduction in daily reduction false positives to 40%. And that concludes my presentation. Back to you, Paul.
Very good. Thank you very much, Mohit. So if anyone has any questions, please pose them in the Q&A section. I'm not seeing any there. Yeah. Okay. Okay, so I'll continue with my piece. Okay. Okay, so I'm going to talk about running the trials, and this is basically the customer value section of the model I showed you earlier. So I'm going to talk about the mobile app and how the mobile app works, and how we receive feedback from the farmer. So the retraining of the models that Mohit spoke about is automated via the feedback from the farmer with the mobile app. I'm going to talk a little bit about our trials also, the scale of them, and some early results that we've received from them. So first off, I'll just share I have the mobile app running on a demo set of data, which I can show with you, and I have it running in an Android emulator on my desktop. Okay, so here we see the mobile app. So this is just basically a help file. Currently, if you go to home here, this isn't populated with any data, but I'll populate that in a couple of minutes. This is just demo data, like this is not based on any real data from the farm. But just go through some of the settings here. So you can set up multiple farms on this, and you can select which is the current farm here. You can set notifications for each of those farms. I just have it set for the demo data farm at the moment. You also have multiple languages here. So we had trials in Portugal and also in Israel. So we have Portuguese, and this just turns everything into Portuguese. So you get your help file in Portuguese, and similarly in Hebrew. Now Hebrew becomes a bit of an issue for me because, well, Portuguese is Western language and I can follow it quite easily. Hebrew is right to left language and everything goes in the other direction on the screen. But for our purposes anyway, we'll go in English. So obviously this is this depends on, this is automatically selected depending on the language of the device in use. So the app is available on Android, iOS, and we also have a web app version of it. So at the moment, this is not populated. Like this is empty. So I'll just remove that for a moment, and I will run the demo script in the background, and you will see some. So we received some alerts here. So basically, we run scripts in the background on a nightly basis for each of our trial farms. And the farmer receives, on the mobile app, receives notifications such as this. So if I click in here now, I should see, yeah, that's just, that's typical, isn't it? Okay, so this is the web app version of it. I have no idea why the Android app didn't work there. So basically, this is the same app, and this is the data that we've just generated. So the farmer receives these set of alerts. He can then, for each of these, like these are the lameness detections that we've indicated to the farmer. So the farmer can either confirm or reject these. If the farmer confirms, he could say that he's given the option to select which type of the degree of lameness. So this is a standard locomotion score in various animals. So in this case, let's say I'll select that this animal is fully lame. So this entry then turns red. So the farmer has this is now marked as lame. So the farmer can look down in the graph of activity, and this might give him some indication as to how the lameness occurred. So on the red lines here, for each of this lying time, steps per day, and the swaps per day, this is the herd mean, and this blue line here is the actual animal that we're looking at, which is 1920. So in this case, in this area here, that might indicate why this animal has been detected as lame. Now, when the farmer looks at the animals, he may decide that, no, this one particularly isn't lame. So if I reject this one, he's saying, yes, this one is not lame. But we have, and this was one of the featured feedbacks we received from some of our farms, could there be another reason to cause this alert? And what we discovered was that a lot of what we initially thought were false positives weren't actually false positives, but they were indicative of other health problems. And so we added this feature based on what was requested from our farms in Israel, whereby the farmer can now indicate the other health issue other than lameness. So in this case, I'm rejecting it, but I'm saying that it's a retained placenta. So we're capturing this data now as future data. So that one actually disappears then from the view. So the farmer can also select by views. So some of these larger farms have the herds are broken down into multiple groups, and we can actually filter by those groups. Okay, so also there's the instance whereby we didn't actually capture the lameness, and the farmer may have a lame animal, but needs to add that in there. So this is one that we've missed. So the farmer can add this in here. This is a slightly older version of the app that's on the Android app. So if I add that in there, this one then gets added at the bottom. So this is, we use this as for retraining. So all of this feedback is used to retrain the models. And similarly, like the farmer can look at the graph here to see how that animal has been, the activity of that animal over the period. So that's in a nutshell how the app works. I'm now going to go back to my presentation and show some more details about the trials. So I will, a moment. Okay. Okay, so we also have a vendor dashboard. This is the view of the vendor dashboard where this is from ENGS's viewpoint. So they have multiple farms here, and they can click down into the farm, see the activities on the farm, what the farmer sees, view this across all their deployments. This could be filtered by which ones have been detected by our system, which ones have been missed, what's currently active, which are complete, etc. So then just to speak of the trials. So in terms of trials, we have two vendors. One is ENGS, and I see Eyal is on the call, so we'll get his feedback from on the ground after my section here. So we have ENGS, who have long-range pedometers on the animals, and we have Herdsy, who have collar-based tracking on the animals. So the initial models that we developed, as Mohit described, were done with ENGS on a previous project. And we initially used those models to deploy on the individual trials. So in September, October, we had, for ENGS, we had 4 deployments. We had one farm in Ireland, which has 122 cows. We had 2 farms in Israel, one with 475 cows tagged, 25 bulls tagged, and the second farm with 140 cows tagged and 18 bulls tagged. And we also have a farm in the Azores with 121 cows tagged. From Herdsy's point of view, we have a farm in South Africa with 60 beef animals tagged, but we did have some Sigfox coverage issues there, so we weren't receiving data from that farm initially. And everything was going quite well, reasonably well. I mean, we were receiving good feedback from the Irish farm. We didn't at this stage have the multiple language support in the app, so we weren't receiving much feedback from the Israel and Azores farm. And we weren't receiving at this stage any data from the South African deployment because of Sigfox issues. But then, of course, in early 2020, COVID happened, and COVID had significant impacts on us. So we had no access to sites across all our trials. Now in South Africa, the Sigfox coverage issues had been resolved at this stage, but we couldn't replace the hardware on the farm, so we couldn't get access to the farm. We also had issues in the Azores, whereby the representative from ENGS's distributor, who was in contact with the farmer in the Azores, was working out of Porto, and he wasn't permitted to fly into the Azores, so we had some access issues there. So in June 2020, we replaced the 2 Israel farms with the farms that we initially had. We didn't receive great feedback from the farmers, so we re-rolled out our trials onto one dairy farm with 460 cows and another dairy farm with 580 cows. And at Herdsy, we still had no access to the South African farm, so we moved to a small Irish beef farm in Tipperary, where we have 55 animals tagged. So feedback. Feedback from the users was very useful in helping us develop some of the app features, such as where we were filtering by the group, and also those detections that were what we had initially thought were false positive detections, but were actually indicative of other health issues. This was very useful feedback that we received from the farms and helped us include that feature in it. So that's our kind of next step going forward, is to use that data to move from a binary classification system for lameness detection to more of a multi-health classification detection system. So from our farmer in Ireland, this is some of the feedback we had him. He said that we were capturing the lameness of animals where only the mildness of lameness actually existed. He was very happy with the app. He said it was done well and easy to use. In terms of results, we're currently collecting our KPIs from the individual trials, but I have some early results here. This is one of the milk yield result from one of the farms in Israel, where we had over the 5 months from June to October compared this year with last year, a 1.7% increase in yield. And on the other farm we have in Israel, we actually have a 7.2% increase in yield over that period. Now on the Irish farm, I don't actually have the charts per se. I'm speaking with Ivan tomorrow about actually getting the detail on the data, but he's indicated a 6% increase in yield over the trial period. So that's a great result. From Herdsy, well, given the short time frame that we had, low instances of lameness in the young herd. I think there were only 3 instances of lameness over the period. So it was, and other reasons are, like, our initial model was based on a different data set and a different data profile than we're receiving from the Herdsy data. So the farmer has stated, though, that he has his best year. Now, this is probably not directly related to the technology, but he did say that the technology encouraged him to more closely track his herd, and he was more aware of lameness in the herd. So we hope to continue these trials. We hope to expand the trials with ENGS in early 21, and we're also in discussion with HERDSI in terms of continuing the trials and expanding their trials, expanding trials with HERDSI and also expanding with ENGS. So that's, I just remind people, like, if you have some questions, please put them in the Q&A. So I'd like to just hand over now to Eyal, who's going to give us an end user perspective. I'll stop sharing now. So Eyal, if you could switch your video on.
Hello, everyone.
The floor is yours, Eyal. Off you go.
Yeah, we just a little bit of a feedback. I was not able to follow everything you've said. Paul has some noise here, but I guess you mentioned it. One of the greatest things here were that there are very little, if any, false alerts in terms of something that is going on. It's not always lameness. Sometimes it's an early stage where you have little or nothing you can do about it. But the information is eventually brings you into a state of mind of being proactive. And in the farm environment, the difference between being proactive and being the one just facing your bottlenecks and absorbing the damage is huge. This is that's the line between a successful farm and a struggling farm. When you have such a tool that provides you in real time the information with a very low, which is very important, because otherwise on save time it will waste your time, but with a very low false positives in terms of there is nothing you can do about it, but whatever. And I did saw you mentioned the feedback of the farmers regarding, well, yeah, there is something going on. We need the method to report what's going on, because this is a great tool. And again, the amount of false positives, as long as it's below a certain level of, let's say, in terms of efficiency of time spending and time consumption, then the tool is something that will help you in no time improve your numbers. Because if you treat a cow, what we saw basically is that between the second and the third locomotion score, this is where we lose them. And this is actually the period, the subclinical period, the period where it's not easy to detect those animals. And this is exactly where such a feature, such as technology, would help us face the situation. And eventually the increased milk that you've mentioned, I guess it's also due to reducing suffer, reducing and being there as possible, treat the animal and make sure that, and obviously from the moment we are treating him, we're treating it, then we will also follow it. So with a very close attention and a very early detection and treatment, eventually those cows, because we know here in Israel at least, we've quantified it, every day of lameness would cost us up to 64 kilos per lactation. So if we are saving those animals and we are helping those animals and we are early detecting those animals, then we will eventually lose less milk. And the effect of it, of being a proactive, seeing your cows as fast as possible, is more than just the milk production. It will reflect also on the fertility index, obviously, because we know that a lame cow is not able to express estrus, for example. So knowing what's going on with it, I wouldn't expect it to express estrus. I will first treat it, and then I will deal with my, let's say, reproductive issues, heat detection, and so on. But I can't expect those animals to express estrus behavior if they are hardly standing. So the effect of flagging, pinpointing animals with issues in real time, and helping the farmer to adopt that so-called proactive approach would be more than just lameness, more than just detecting the lame cows, and it would obviously affect almost all aspects. Uh, Lameness is one of the main three causes we lose cows. It would be reproductive, it will be mastitis, and it will be lameness. But almost all those issues are correlated one with each other. Obviously, reproductive is because the cow is not expressing or not conceiving or losing the embryon due to the situation, the health situation she's in it. And such an information, such an application in real time helps you always be on the same page, let's say, with the overall performance and the health status of your herd.
Thank you very much, Eyal. Very, very interesting. Always good to get a good on the ground viewpoint and feedback. Thank you. And thank you for, I know you're in meetings and I know you've taken time out to join us today, and I really, really appreciate it. Thank you very much.
Great, thank you.
So I just have some open questions here for Mohit from Mohammed Taj al-Din.
Yeah.
So he has, do you see the questions, Mohit? So yeah, just for the benefit of the audience, I'll just read the first question. What is the amount of validation data used and the percentage compared to the training data?
Yeah, so I will answer them one by one. So let me go the first one. So when the Smart Herd project, which is the background of MELD, when it started, so the validation data used was 10%. When MELD came into picture, the validation data used while retraining was 30%. But once your model is in production, once you basically have at least a satisfactory performance, like what Eyal mentioned, once that goes into production, all the data, the production data that is now coming, that the whole thing actually acts as validation data if you're gonna retrain the system again. So one of the reasons for this thing is, like, with methodologies such as KNN or even linear regression, there is no actual concept of partial fit where you will say that you will just retrain the hyperparameters without the data. So you need to have the data as well to basically reduce these false positive. And let me answer the next question from Messiah first. False positive was 40%. It would be a little bit higher. So do you have any idea how to reduce this? So false positive was not 40% actually. So the way that I represented over there was that when we started the fall, we reduced the false positive by 40%. So I was probably a little bit not clear in my presentation. I answered the next question, Paul, if you can see. Yeah. So now coming back to Mohammed's next question. So the next question from Mohammed is, which ML model showed better accuracy and to which degree it can be applied to new herds? And then the corresponding question is, do you anticipate using deep learning models can better detect lameness? So which ML model showed better accuracy? So there were three models that showed better accuracy. The first one was KNN with specific hyperparameters. So the main hyperparameter was the value of K, which most of the time for most of the herd stayed at K equals to 4. But for other herds which have different farming practices, such as which are grouped together in barns already, so for them, this lameness transition probability approach, where you use regression, where you pose the problem as a regression problem, and then you use the basically return probability as the index for saying, classifying it as 0 or 1. And that acted better, and which is mainly, this farming practice was mainly mainly followed in Israel. And then to which degree it can be applied to new herds. If to my understanding, which I understand if this question correctly, so degree when it comes is like, given a herd size, what would be the accuracy to classify the herd into two profiles, which would be non-lame profile and lame profile. So currently that accuracy stays at 89%. Now the next part to that is, if you once you do this part and then you take a single animal, and then that single animal has been classified as lame. So what is the confidence level, or what is the accuracy for that particular animal to be saying that that animal is surely to be lame? So currently that confidence interval stays at 89% plus minus 2.5%, so which is the 95% interval for each and individual animal. The next question is, do you anticipate using deep learning models can better detect lameness? Ideally, the way, to my limited experience with machine learning and deep learning methodologies, yes, they can detect lameness better, but ideally you would need a larger feature space, to my understanding, to do that. With 3 feature space, the classical machine learning models, or machine learning models which can be used to for the specific fit to the specific problem, they still probably serve better as compared to, and while keeping these constraints of computing capacity in mind, that for deep learning, as long as you increase your network layer, your computing capacity or the computing power of your model increases. But at the same time, to use those models, you need to have larger data set, and not only the larger data set, you should have ideally a larger feature space as well. And the last question is, what parameters and weights in the model are adjusted per herd? So the parameters that are adjusted is that herd for KNN is mainly K. Most of the herds whose herd size is greater than 43, that parameter or the hyperparameter K stayed the same. Uh, the weights that we talk about, I think the weights are usually concerned with when you talk about neural networks, but in case of regression, in regression, the Lameness transition probability approach, these are the regression coefficients. So those are the ones that are changed after iterative feedback, and usually that iterative feedback is at least 14 days for us to basically do any kind of retraining on the selected model per farm. I think all of these are.
Yeah, that's great, Mohit. That's great. I'm just looking here.
If there is any follow-up question, please feel free to ask.
I don't see any further questions there. Yeah.
And I hope we answered the question of which was the false positive was 40%. So that was not actually 40%. We reduced it to
yeah.
40%.
Okay. So thank you all for your time. We've just about made it on just slightly over the 45 minutes that we had assigned to this. So I'd like to thank you all. I'll probably send a short survey to get a feedback on your experience of the webinar in the next 24 hours. So I'd very much appreciate it if you could fill that out for us. Thank you, Mohit, and thank you, Ayal, even though he's already left. And thank you all for joining us, and thank you.